And without further ado, part two. Louis Morel, Haas member, holds a BS in biochemistry from McGill University and an MS in food science from Michigan State University. He worked in the food industry for more than 3 decades. He contributed to the development of a food science course for high school students. Let's welcome Louis back again. Thank you.
Thank you. And welcome back, those of you who were here last week for part 3 of this series on remarkable women scientists. And welcome to the ones who were not here for the first time, perhaps. You will undoubtedly uncover some trends this morning. There's been one common thread through all of this over time, over several centuries, you could argue millennia. Women have not been treated very well when it comes to academia or in the sciences, and there will be a bit more of that this morning. There will be other trends as well. You're going to be introduced to some women who were the first ones to accomplish certain things in their fields. So hopefully you will find this interesting. So some more of these challenges. And now before we get to the actual accomplishments of some of these women, I want to just do a little bit of historical context. So between the fall of the Roman Empire, which happened near the end of the 5th century, and the time that the Turks took over Constantinople, which is Istanbul today, near the end or the middle of the 15th century, in that millennium, we call that the Dark Ages. And there were a lot of characteristics throughout that time period, and that included the treatment of women. So generally speaking, the men were misogynistic. Women did not have much of an opportunity to have any kind of education. They weren't expected to be able to read or write. They remained largely illiterate. Girls who wanted to learn, or their parents who wanted them to learn, would send them to a convent. More about that in a moment. And perhaps in a nunnery or convent, they could learn there. And many of those women probably ended up in religious life. They didn't turn out to be scientists. Well, that's not surprising, because during this millennium, there were very few advances, certainly in the Western world, regarding science and art. And I point out the Western world because starting, even at the end of the 10th century, but in the beginning of the 2nd millennium, the Arabs were actually pushing forward with mathematics and astronomy, but they were totally isolated from the Western world, where they were truly living in the Dark Ages. There were a number of rulers and influential people who did not help the cause of women, and you're familiar with all these people. We can start with Martin Luther in the beginning of the 16th century. As he was proposing his own theories, he was totally opposed to girls getting an education. So that did not help their cause either. And as you know, Luther was extremely influential in certain parts of Europe. Good old King Henry VIII, excuse me, was a despot and how shall I put, well, a strong-armed ruler. And he actually, during his activities, destroyed convents. So that meant that there were even fewer places for girls to learn. And this happened in the beginning of the 16th century. And one of his successors, Queen Elizabeth I, even though she was liked by her subjects, by and large, her activities, her rule did not really improve the status of women. So through this period, as the Dark Ages have ended in Europe, there isn't any real movement here to improve the life of girls and women in general, except in the Italian peninsula. So as the Dark Ages get enlightened, a lot of scholars are gravitating towards the Italian, well, actually, it wasn't quite Italian yet, but towards the city-states, the kingdoms, the duchies that made up what is now Italy. Italy would not become a country, a unified country, until 1861. Before that, there were a lot of political enemies, geopolitical wars, but there was also a lot of liberalism in these areas. So they succeeded in attracting scholars to come to places like Bologna and Rome and Pisa and Florence, and they were able to foster an environment that promoted culture and also science. There were some women who became famous because of their endeavors in the arts, in science, in medicine, but it was pretty much restricted to this part of Europe, as you will find out. And you can easily remember many people who flourished in this environment, most of them men. So today we'll talk a little bit about some of these women who came out of this movement very briefly, and then I'll focus on three individuals: Sofia Kovalevska, Rita Levi-Montalcini, and Barbara McClintock. And none of those names are necessarily household names, but as you'll find out, they were quite prominent in their fields. So the Dark Ages are over. In Italy, primarily, there is this period that we call the Renaissance, which is a French word which truly means a rebirth. During this time, there's a shift in thought and how to promote culture, starting in what is now Italy. Part of it had to do with the fact that this German, Gutenberg, had invented, and I put that in quotation marks, had invented the printing press. Actually, he had not. The Chinese had actually invented the printing press long before he did. The idea of the printing press didn't come immediately to Europe. About 150 years or more elapsed before that happened. Now, I remember many years ago at a World's Fair in the Korean pavilion, they claimed that they invented the printing press, not the Chinese. And I don't think we're going to solve that here today. The fact is that it did start in Asia, eventually found its way to Europe. Gutenberg perfected it and used movable type. Why was this important? Well, all of a sudden, you've got a way to disseminate information in book form, and you can distribute it broadly across the lands, and you can make more people aware and able to learn from these printed books. Also at that time, there was a guy in Italy called Galileo, and he was very influential. He was at the University of Pisa working on his theories, and he was an experimentalist. And he was putting forth some ideas that were quite radical. This was because for the past 1,500 years almost, people were focused on what Aristotle had said. And they believed that Aristotle's laws applied. But Galileo had other ideas. And through his experiments, he demonstrated that it wasn't all true. And this illustration here on the right of the slide shows a public demonstration that Galileo had in Pisa at the time. So he's standing on the balcony, on the ledge. He's going to drop a cannonball and a wooden ball, and he's going to demonstrate that they're going to land at the same time. Aristotle didn't say that. He said that the cannonball is going to go much faster than the wooden ball. But Aristotle never experimented with that. Galileo did. And as it turns out, because of Galileo's experiments, he knew that they would accelerate at the same speed and that they would indeed land at the same time. Turns out that Aristotle was wrong. So now we're starting to contradict very long-standing precepts. And it's going to be a catalyst to start to look for other areas where we need to learn. One of the women who during this period had some influence was Elena Cornaro Piscopia. As you can see, she lived near the end of the 17th century, had a short life, and her father was a much more liberal father than others you will meet today, and he sent her to the University of Padua. As you can see, Padua had been around already for 4 centuries, one of the oldest universities, and certainly one of the most respected universities in Europe at the time. Elena had an aptitude for languages, spoke 8 of them. We learned, again last week, we learned of another European who had the opportunity to learn languages. So did she. And she studied theology and mathematics. Now, keep in mind that this is a woman, and women don't do these things so much. So we're in the middle or end of the 17th century now. And in fact, in 1678, she was awarded what was called then a doctorate. It's not like a doctorate that we know today. Anybody who completed university studies at that time obtained a doctorate. Regardless, it was quite an achievement for a woman to do this. Now, this doctorate wasn't in sciences, it was in philosophy. But it was such an accomplishment that on graduation day, which was supposed to be held in the cathedral, there was such a large crowd, they couldn't all fit in there. Because a woman was getting a degree, people came to see this. They had to gather elsewhere, outdoors, and award the diplomas there. She was the first recorded woman to earn an academic title. So here we are near the end of the 17th century, and we are in liberal Italian country. So they're starting to accept that. But it took a long time for the next woman to get a degree. It was not something that was very popular. Women were not expected to become professionals, and they weren't expected to become literate and get these degrees. It's unclear whether or not the university offered her a job in mathematics or not afterwards. But what we do know is that she was a devout woman, and she did a lot of charitable work for the poor and the sick until her death, which, remember, came very quickly. She died at the age of 42. Google honored her on one of her birthdays, and though this particular image doesn't tell us a whole lot about her other than she was a learned woman and clearly was able to study in several languages, and that's represented here perhaps with this image. We will see another image later from Google that is much more descriptive of what the individual did. Near the end of the 17th century, Clelia Borromeo was born, and she too had aptitude for languages. There seems to be a trend here. She became a prominent mathematician, and it is said that when she was presented with any mathematical problem at the time, there isn't one that she couldn't solve. She was that good at mathematics. Certainly a very unique and seldom seen trait among women. She was considered eccentric because she was so independent, especially for a woman. This was unheard of in society at the time. And because of her stature and because of her knowledge in mathematics and in physics as well, she founded her own school, the Holland Academy, and she did this in Milan. And if you were here last week and you remember, in the case of Maria Agnesi, I mentioned that Luigi Grandi was a mathematician at the beginning of the 18th century, and that she had continued some of his work. Well, Grandi was a frequent visitor to the school that Borromeo had founded. So there's a connection here. In the school, very much like Maria Agnesi, she also tried to teach Newtonian physics, keeping in mind that Isaac Newton, was essentially a contemporary, and that she believed in his work, his physics, his mathematics. And that is what she presented at the school in the curriculum, and the philosophy and mathematics of the German mathematician Leibniz. So she had become quite well known in her time as well, being a very unique woman. So was Laura Bassi. She is the second woman to be honored with a doctorate, as I explained earlier. She graduated from a university, and this time it was not just in philosophy. The university gave her her degree for natural sciences. So now there's the first trend here that we're actually talking about a woman getting a degree in the sciences. She's the first one to achieve that. She was given a job at the University of Bologna because Archbishop Lambertini, who was part of our conversation last week, he would eventually become Pope Benedict XIV, was very influential. And if you recall, the clergy had influence in the Catholic universities as to who was appointed to teach. So Archbishop Lambertini recommended her because of her knowledge that she become a teacher at the university, and she's the first woman to actually get a paying job at the university to teach. She was a versatile scientist. She dabbled in physics, in mathematics, in hydraulics, and also in mechanics. She was recognized for her talent and was elected to the Academy of Sciences of the Institute of Bologna in 1732. Again, a first. At that time, the Royal Society in London, that included people like Newton, and the French Académie des Sciences in Paris, they were all male. They had not yet accepted any female, partly because none of those universities in those countries, including Germany, accepted women. So they didn't have the opportunity to develop women students who could become famous scientists, influential scientists, or mathematicians and be admitted to the academies. But the Academy of Sciences in Bologna did accept her. And she too opened a school, and she too embraced the philosophy and the work of Isaac Newton, and she focused on his work in particular when she and other people taught in her school. Google also gave her a doodle to honor her. And I want to point out here, and for those of you at home that aren't seeing this, my cursor, the graph on the left is a simple line that starts at the origin. And this is a graph of force as a function of mass, and the slope of the line is the acceleration. This is in concordance with Newton's second law. So the artist who drew this thought of that, and on the right, I suspect that these balls that are suspended are representing mass. And I'm only interpreting here why the artist would have done this, but you could argue that this array of masses to the side of the graph is to tell us that it's independent of mass, that the acceleration is constant. And that's what this graph is showing us. So that is another Google Doodle that came out for an anniversary of this individual. Now we're going to be in the middle of the 18th century. So we've moved forward in time. The times they are changing. And Maria Ardinghelli developed into quite a mathematician and physicist, but that's not really why she's remembered, interestingly enough. Stephen Hales was a physiologist in England, a plant physiologist in particular, and he lived at the beginning of the 18th century. Hales was an experimentalist, and he is remembered largely because of his experiments with certain plants as he was studying the pressure developed by the sap in plants and trying to determine and prove the direction of flow of liquids in a plant. It wasn't obvious to everyone that the root system was important and how the water and the sap traveled in the plant. Remember, this is beginning of 18th century. So Hales wrote a famous book that he called vegetable statics. And statics came from a Latin word that had been used in the literature before, statica, and it had to do with the pressure of the fluid. In this case, it's water. And he also wrote hemostatics, which had to do with the blood pressure of in organisms. A man named Poiseuille, a French physicist, later would examine blood pressure and blood flow in great detail. And we remember him he quite well in certain aspects of physics. And Ardinghelli did not examine these areas specifically, but she was influenced by contemporaries. You may recognize these names: Cavendish and Priestley, the British chemists, and Lavoisier, the French chemist. So these were all contemporaries, and she certainly was influenced by them. But we remember her mostly because she was a translator. This is the cover page of the book that Hales wrote, and it's a very long title, Vegetable Statics, or an account of some statical experiments on the sap in vegetables, being an essay towards a natural history of vegetation. Well, it turned out that that very long title did not dissuade people from purchasing and reading the book. It was a very well-known, very well-distributed book in the beginning of the 18th century. However, when Maria translated the book, it was half a century later, and she had an Italian version of the same book, and the cover does talk about Stephen Hales, and her name appears as the translator, and the book was published in 1776. And this is why we remember her mostly as the translator. This brings us to our first, more contemporary, perhaps, remarkable scientist, Sofia Kovalevskaya. She was born in the middle of the 19th century in Russia. So keep that in mind. The context is Tsarist Russia. She was born in Moscow, and her family had a mansion in St. Petersburg, and that's because the family was relatively wealthy, certainly quite affluent. Her grandfather was a mathematician. In fact, he had worked for the Russian Topographical Corps, so he had some prestige, some influence. He was working for the government, as it were. Her father was a Russian general, and that will have a lot of importance on her life. Very strict rule, military rule in the family. He took his role as patriarch very seriously. The family, as I said, was quite wealthy, so that allowed Dad to hire tutors for her and to allow her to learn mathematics from tutors. She had been influenced this way because her uncle Peter was knowledgeable in two areas. One, in mathematics, and they had conversations which stimulated her brain and her interest in mathematics. But he also, this is the 1860s now, 1850s, he also had socialist ideas. And remember the context. There's a czar in Russia, and socialism isn't really what the czar wants to hear about. But it would influence her as well in her later years. There is this anecdote of interest. The family was wallpapering, or perhaps replacing wallpaper with new wallpaper in their house. They had one room left and they ran out. And they probably couldn't run to the corner hardware store to purchase more. So the father, at least as an interim solution, brought home some papers that had been printed and put them up on the wall. It turns out that the printing on these papers were from a calculus book. And this 9-year-old girl, Sophia, is reading this, trying to make sense of it. And she does. She actually gets to understand the mathematics involved here, which will serve her well later. So she literally read the writing on the wall. And it served her well, as you will find out. But as I mentioned earlier, most of Europe refused women in universities. Russia was no different, especially because they were single women. That was not a place for them at a university. Also in Russia, single women could not travel abroad. They needed permission from their father to have a passport to travel. And her father would not let her travel anywhere, not outside of Russia. So that disappointed her as well. Her father did not want her to pursue a career in mathematics either. That is not what young girls did. So he was opposed to that as well. You can imagine there's a little bit of tension and friction between father and daughter here. So she was interested in this movement in Russia that wanted to provide equality to women, to have freedom of marriage, no fixed marriages, to be able to choose to divorce when you wanted to, and also, perhaps more importantly, the right to education. So she was very keen on these precepts and also wanted to go to university. She is, as I said before, because of her Uncle Peter's ideas, she was very sympathetic to these ideas of socialism that were beginning to burgeon in Russia. But she can't travel where she wants to go. She wants to go to university. So what is a girl to do? There's one easy answer: get a husband. She needs a passport, and only her father or her husband can sign the forms so that the government can issue a passport to her. Easy, isn't it? So she did that. And her sister, by the way, her younger sister, was also complicit to all this because she too wanted to go study in Europe, and she too wanted to have this kind of freedom. But the sisters figured that Sophia had a better chance of success. So she did actually choose a husband. It was a student at the University of Moscow. He studied biology and paleontology. His name was Vladimir Kovalevsky. This is a picture or an illustration of him from later in life. But he actually liked her. He liked her because she was fluent in languages, because she was fluent in mathematics, and he had a scientific mind as well. So there was some compatibility there. However, even though they got married when she was 18 years old and had the ability to get a passport and to travel outside of Russia, they had a rather unremarkable platonic relationship. And they, in fact, they moved to St. Petersburg after they were married. And she thought that she wanted to be a physician, so she was enrolled in medicine. Turns out she didn't like anatomy. And that was some way to dissuade her from pursuing those studies. But she had this interest in mathematics. So she did that. And as she put forth the argument that she should be in the mathematics department, she proved to the teachers that she was indeed very talented, partly because she had learned at a young age what calculus was, and it was self-taught. So her teachers were impressed, and they accepted her for that. So it's 1868. She's 18 years old. Vladimir and Sophia are married, and they have moved from Moscow to St. Petersburg to study there. Well, that doesn't work out so well. And she really wants to go to Germany, to Heidelberg, to study, because the University of Heidelberg, the oldest German university, is reputed for its quality. And she wants to go to study there, and they move to Heidelberg only to find out that they will not accept a woman. Well, that's a setback. But while she was there, she met some of these faculty members, and some of you will recognize some of these names: the physicist Kirchhoff, the physiologist and physicist Hermann von Helmholtz, and Leonard Königsberger, the mathematician. They were all faculty members. She met them, she impressed them, and she convinced them that she could audit their courses, even though she wasn't a student. So they accepted to do that, and they actually allowed her to do it. And she spent her time at the university as an auditor of sorts. Well, Königsberger was a student of a famous mathematician at the University of Berlin, Karl Weierstrass, and you can see his image on the right there. He recommended Sophia to Weierstrass, and she went to Berlin in the hopes of being his student, but the University of Berlin refused to admit her. Are you sensing a trend here? It was commonplace in Europe for almost every university, except in a few Italian ones, Bologna being an exception, to refuse women at the time. They would not be admitted as students at universities. But Weierstrass, because she had been recommended by Königsberger, he listened to her and he gave her a set of advanced problems that he would have given to his students. And he was astonished at how well she responded. And she got correct answers, even though she didn't have the same formation that he thought she had. So he was very impressed. So he recommended to the university administrators to admit her. They refused. So the university is not going to give her a place to study. And for 4 years, Weierstrass accepted to give her private lessons. He felt that she was such a talent in mathematics. As it turned out, she was. And after the 4 years, she presented her dissertation on the theory of partial differential equations, and it earned her a doctorate. And she will be remembered largely because of her knowledge and development of partial differential equations. So that's her legacy. She was the first woman to get a doctorate in mathematics. So this trend of firsts continues with her. But she also learned, as we know, life is not fair. She moves from Berlin back to Russia. Now she's got this degree in mathematics, and it doesn't help her. No one will hire her to teach mathematics. She's a woman. So instead, she wrote articles. She wrote a short novel. She will write a few things about Russian life as she gets older. And because of her socialist tendencies, she is preoccupied by women's rights, and she has been slighted many times already. So she's a first-hand observer of what is going on in society, and she's not happy about it. Vladimir and her had a daughter in 1878, so now Sophia is 28 years old. She has a daughter, and her husband, paleontologist, biologist, he's working, but on the side, he has some business endeavors. And things go sour. There's a stock scandal. He's involved in it. He's depressed. He's not sure what he's going to do. Life continues for a while, but it doesn't take too long. 5 years later, Vladimir, in total despair, takes his own life. So now, Sophia is a widow. She has a 5-year-old daughter, and she still wants to pursue a career in mathematics. By this time, she had gone back to Berlin, and she was working at the university studying the refraction of light. So she's totally engaged in this, but now she has a different burden to take care of. She's got a daughter as well. So as I said, for her, life has not been very fair. Meanwhile, totally separate from this, a German named Gustav Mittag-Leffler has been hired by the administration of a new university in Sweden, in Stockholm. And he wants to bring a great mathematician to the university. And he wants it to be a woman. So is this part of Swedish Enlightenment? Is it just him? Is it a new trend? So he actually convinces her to come to Stockholm. And now it's 1883, and she is going to teach differential equations in Stockholm. And she does it in German the first year. Remember, she's Russian. She knows German. She has been studying in Berlin and elsewhere in Germany. So she starts in German, but she has to learn Swedish. And in her second and third years, she teaches differential equations in Swedish at this new university. But because she's a woman and just because she'd been hired did not guarantee that she would be accepted easily. And in fact, she wasn't. There was a lot of resistance among the faculty, and it took 5 years for her to get tenure at the university, but she did get it. So there is that, but it was a difficult process for her to do this. She did a lot of things. So remember 1883, she's in Stockholm, and now there's a new journal that still exists today called Acta Mathematica. And she became the editor of the journal. This is quite an accomplishment. There's a woman at the head of this mathematical journal. This was unheard of. So this is, again, another first for her. And because of her prowess in mathematics, she was encouraged to participate in a contest that the French Académie des Sciences in Paris subsidized every year. The Prix Bourdin, named after the man who donated the funds for it, certainly was the most prestigious honor in mathematics in the late 19th century. And the way this worked, there would be a competition to solve a problem, to submit answers, and for these projects in sealed envelopes. The judges would assess and evaluate all of these submissions on their own merits blindly, not knowing who the author was. So she submitted her work on the rotation of a solid body, and you'll see an illustration of that later, about a fixed point. And when the judges read this, they thought that the quality of the solution was so high that they increased the prize money from 3,000 francs to 5,000 francs. Then they unsealed the envelope to find out who the author was. It was this Russian woman, Sofia Kovalevsky. So I'm sure that shocked a lot of people, but that's what happened at that time. So she won the Prix Bourdin, and luckily for her, with an increase in prize money. By 1989, the following year, she received a lifetime appointment at the University of Stockholm. So think of this. At first, she's the first woman there at the new university. She's tolerated probably by the men who are teaching there. And she doesn't get tenure early on. It takes 5 years for her to get it. And now she's a member of the faculty, but now she's won the Prix Bourdin. All of a sudden, she has been elevated in stature. And now she gets a lifetime appointment to teach in Stockholm. And the same year, the Imperial Academy of Sciences changed the rules so that they could actually elect a woman to be a member. So remember, the Royal Society in London hasn't done this yet. L'Académie des Sciences hasn't done it, but now there's starting to be a change in trends. And the Imperial Academy of Sciences did accept her. However, she couldn't go to the meetings. She wasn't allowed to attend because they didn't have women in those meetings. Only men were allowed to attend. So did I mention that her life was not fair? So she and other women kept coming up to these obstacles all the time. And it was frustrating, to say the least, unfair, but it was a reality that they had to contend with. Now, remember that she could not study in a Russian university because she was a woman, but now that she's been honored with all these awards, and now she's got a lifetime appointment at the University of Stockholm, the Russians take notice. And the Russian Academy of Sciences, they decide that they're going to name her corresponding member of the Academy. She's not in Russia, she's in Sweden. So they give her this title and essentially bring her into the fold. But is it more of an honorary degree than anything else? Yes, perhaps. But at least she's been recognized by the Russian community. So those were some of her accomplishments. I mentioned that she did not live very long. She died of pneumonia in Stockholm. The story goes that she had gone back to Russia for some trip, and on the way back to Sweden, contracted the pneumonia and died from it shortly after she got back to Sweden. So that was the life of Sophia. Leopold Kronecker was a very well-known mathematician in the middle of the 19th century. And later in his life, he wrote that the history of mathematics will speak of her, Sophia, as one of the rarest investigators. High praise, giving her the claim that she was so good at what she was doing in mathematics, and she had accomplished so much. Well, it turns out that Leopold's words really were for nothing because it didn't happen. In fact, Kovalevsky is not remembered that well in the community. So he thought that she would be elevated to be a very prominent mathematician. And while today we remember her, at the time that did not happen. The Soviets issued this stamp for her in 1951. And at the bottom, underneath her portrait, her name appears on the first line, and then the rest reads, Outstanding Russian Mathematician. So in the middle of the 20th century, the Soviet government recognized her as part of their Outstanding Russian Scientists series. And not to be outdone, the following year, the Soviets also issued a stamp for her husband, Vladimir. And while his name appears under his portrait, at the top of the postage stamp, it reads Outstanding Russian Scientist, Biologist, Paleontologist. So they were both honored by the Soviets on postage stamps at the beginning of the 1950s. Google also honored her, and there are some interesting traits to look at here. So first of all, the background, all those X's, that's part of some of the differential equations that she had worked on. The image in the middle O has to do with the rotation about a solid body. That was the dissertation that she offered at the University of Berlin. Her portrait is there, but one little known fact, Google, for whatever reason, only presented this particular doodle in Russia. I do not know why they did not extend it to other countries. And I take it none of you knows what Google's modus operandi is, but only the Russians got to see this when they were looking for information on Google. So there you have it. And again, perhaps that is unfair, but that was her life, wasn't it? Yes, Susan.
So, Louis, how did you find it? Do you speak Russian?
Yet. I looked for doodles in general, and the Google site lists them. If you're interested in this, you can search doodle.google.com, as I recall, but you can easily search it for it on Google. But at that site of Google, you can filter your searches by geography, by year, by science, by topic, and you can get a listing of all the doodles that have appeared that correspond to whatever filters you have done. You can also put the name of the individual in, and it will return the one, or if there are more than one, which there are not many of those, but you can put the name of the event, like International Pumpkin Day or some such thing. Or in this case, you could put in Sofia Kovalevsky, and the doodle will show up. And when it does, it also shows you the map of where the doodle was presented. And the one that I showed you before, Basi, that one was showed throughout Europe and elsewhere. Now, why this one was only shown in Russia, I do not know. So if you're interested in that, you can go to Google and you can look at the doodles, because they often change. There's something every day. Some are more elaborate than others, and some are very specific to celebrate some anniversary or some event. And you can learn a lot about those, and you can also search for them. So that's how I got there. So it wasn't because I can read Cyrillic or speak Russian.
That's so interesting. I always thought doodles were only some kind of a dog.
Dog. Yes,
Thank you. I'm going
yes.
to use this.
right. Um, I think by the way, when you look for a doodle, you will get the name of the artist, and sometimes it's more elaborate. You'll see the progression that the artist had. You'll see some essays. This is the first drawing, second iteration, third iteration, final image. So these are artists, graphic artists that work at Google or submit their work to Google, and they usually give a lot of thought to what they want to represent in the image. So this is one example. You've got her dissertation topic there. You have also what she's famous for, her knowledge of partial differential equations. So it's incorporated into the image. The one that I showed you about Piscopia at the very beginning wasn't so informative. And for those of you who were here last week, I mentioned the postage stamp from the US for the nuclear physicist Qian-Xiang Wu, that it told us nothing about her accomplishments. We saw a lovely photograph of her and the words nuclear physicist. That's it. So something like this is much more informative. It leads us to have some better knowledge of what the individual accomplished. The two postage stamps I just showed you from Russia, the Soviet Union actually, they didn't tell us a whole lot other than their occupation. There was nothing like this in those designs. Now we move to another fascinating individual, not a household name, but I believe that you'll be intrigued by all that she did. Rita Levi-Montalcini is known as the queen of modern neuroscience. And it was difficult to summarize her entire life in only a few minutes. She lived to be 102 years old and remained very, how shall I put this? Her mind, we are told, was still very sharp until the end. And I will point out one anecdote that suggests why. There we go. So she was born in Turin. Yes, another Italian. In 1909, her parents were Jewish. Her father's name was Levi. The mother's name was Montalcini. And for reasons that I ignore, she chose to use the two family names in her own, Levi-Montalcini. She was definitely raised in a Victorian era climate. So father was the patriarch, and he was an electrical engineer, and he didn't think that it was a good idea for women to have professional careers of any kind. His two sisters had doctorates, and both had failed marriages. So with a sampling size of 2, he decreed that his daughter would not have a professional career. Well, it turns out that Rita was a pretty good student, had a lot of aptitude, and the governess for the family that had so much to do with raising the children died of stomach cancer. And that impressed Rita considerably. And she believed that because of that, she would study medicine and she would pursue a career in that field. This is early 20th century, but we are in Italy. And remember, Italy is more liberal than many other countries in Europe at the time. So even though dad said, no, you are not going to proceed with a professional career, he eventually gave in and he let her enroll at the University of Turin in 1930. So she's 21 years old now, and she's at the university. The University of Turin has been around for a long time, as you can see, early 15th century. It's well recognized. And she is an intern in the lab of Giuseppe Levi, and this Levi is not related directly to the father's side of the family. Their father was also a Levi. So she worked in his lab, studying tissues. That's what histology is. And she was told to count nerve cells and to grow nerve tissue in cultures. this kind of work appealed to her, and it developed a passion in her to do research. Interestingly enough, at the university, there were two classmates, Salvador Luria, the one on the left in the picture, and Renato Del Bucco. Both of them would later gain Nobel Prizes for their work. So they were all classmates at the University of Turin. Luria got his work, or his Nobel Prize rather, for his work on the genetic structure of viruses and how they replicated. Meanwhile, Del Bucco, he worked on oncoviruses. These are viruses that cause cancer. So his work was recognized in 1976, only a few years after Luria. So these were classmates of hers, and they all went to great fame later on. So she gets this degree in medicine and surgery in 1936. While she was a student in Turin, her father passed away. So she had to deal with this, but now she has more freedom because dad doesn't have a hold on her anymore. She enrolled in a 3-year specialization program, and she was going to learn more about neurology and psychiatry. So she does this at the Clinic for Nervous and Mental Diseases. At the time, an institute that was well known for its research in this area. Now, while she was a student working in the lab, and later on at the clinic, she developed a tremendous skill for microsurgery and a very important technique called silver staining to stain nerve cells, which became well established and used by others. So this silver staining method was very useful for the kind of work that she was doing, to be able to isolate and identify the nerve cells. But at that time in Italy, things were not going so well. If you remember, 5 years earlier in Germany, the Nazis took over. Hitler and his movement are stirring things up in Germany. Fascism has become of interest in Italy. Mussolini is at the head of the country, and he writes this manifesto. And La Difesa della Razza is the title of a periodical that came out in 1938 and would be published regularly until 1943. And the title, La Difesa della Razza, is actually the defense of the race. The race in question is the Aryan race. And it prohibits non-Aryans, that includes Jews, from pursuing academic and professional careers in Italy. So now she can't keep her job because she's a Jew. So she moves away. She loses her job, and the anti-Semitism movement grows very quickly in Italy. This idea of what's going on in Germany has blossomed with Mussolini in Italy. So she leaves Italy, goes to Brussels to work in a neurological institute there. She's only there for a few months because it's 1939. The Germans have moved into Poland and they're about to move into Belgium. So she packs up and leaves again and goes back to Turin. She wanted to continue her work. She couldn't go to a university or a clinic because she was a Jew. She's been banned from that, as other Jews have as well. That includes Giuseppe Levi, who was her teacher. So he too is enveloped in this developing movement of anti-Semitism. So she decides that she's going to set up her own lab in her bedroom in her house, and she starts experiments. She had been influenced by another European, a Jew who had left at about 6 years earlier. Victor Hamburger had left Germany. He saw the writing on the wall, went to the United States. He got himself a job at Washington University in St. Louis. And he had published a paper in 1934 on the embryology of chicks and I'll explain that in a moment. She had read this paper and had been influenced by what Hamburger had done and wrote. So she too continued to do work with chick embryos because that's what he had worked on. What he had done essentially was to remove surgically the buds of a chicken embryo that would eventually become wings and tried to observe and assess the development of nerve cells afterward. This was important because he observed that nerve cells were growing, and he's postulated that there was some kind of signal in here that was being transmitted to allow the nerves to grow. And she was intrigued by this, so she continued this line of work in her own bedroom. I mentioned that Levy could not keep his job either, so because they had worked together before, he joined her to work in her house to do the experiments. But now it's 1941, and the Italians are embroiled in World War II, and Turin gets bombed by the Allies. So the family has to move again, and they go to the Piedmont area, and there they have a modest place to live in, but she continues her experimentation with the simple instruments that she could use, that she could have brought along or could have acquired. So it's rather rudimentary. But to the astonishment of the farmers around there, she goes and buys eggs from them, but she wants them to be fertilized eggs. She wants the embryo to grow in these eggs. So they're astonished. They don't understand, why do you want fertilized eggs? She said, I want to feed my babies these eggs because they're more nutritious than the regular eggs. Not true, but she got the fertilized eggs because she wanted to grow the embryos and do the experiments on those chick embryos. So that's what she did with the crude equipment that she had. Now it's 1943, and Mussolini resigns, and he would not live much longer. The Nazis have arrived in Turin. So there's no way to go back to Turin, at least not now. So the family moved again from the Piedmont area, this time to Florence. So they're on the run and trying to escape the throes of World War II. Finally, the Allies arrive in Turin in 1944. They liberate the city, and it's possible to eventually go back there. During this particular period, now that the Allies are in this part of Italy, she works at a hospital as a physician to treat soldiers. In May of 1945, the war ends and she can return to Turin. Giuseppe Levy gets his job back at the university. He hires her as his assistant, and they work together for some time on this chick embryo problem. And they published several papers together. And the results that they had became a foundation, as you will see in a moment, for much more studying that was done about nerve cells and their growth. So Victor Hamburger, meanwhile, in St. Louis at Washington University, has read some of her work and Levy's work, and he invites her to come to Washington University for a few months. She accepts because she knows how Hamburger has done his work. She respects it. He respects her work. Great marriage here. So she goes to St. Louis. She was going to be there for 6 months. Turned out she stayed for 30 years. So the question here is, how do nerves growing out of a nervous system in an embryo find the actual limbs or other tissues that have to be innervated? And that's one of the questions that she was trying to answer. Well, Hamburger's experiments with the chick embryos were, as I mentioned, the surgical removal of a wing bud. And when he did that, there was a profound reduction on the operated side. So if he removed the right wing limb, the bud of that wing, that side was not as innervated as the others, as the other side. So he thought that the growth of the nervous system had to depend on the target tissue being there, and that there had to be some kind of signal that was being transmitted to communicate chemically with the other cells. But what was that signal? Hamburger and Montalcini tried to figure this out, and at Washington University at the time, they could not do the tissue cultures that she wanted to do. But she had an acquaintance from Europe named Hertha Meyer, who had been a student of a chemist you may be familiar with named Emil Fischer in Germany. And she had gone to Rio, to the University of Rio there, and had established a tissue culture lab. So that's where she wanted to go, where Rita wanted to go to do the work that she wanted to do, but could not do at Washington University. So in 1952, she goes off to the Institute of Biophysics. She had grafted tumor cells into 2 mice that she brought with her in her handbag to Rio. Now think about this. Today, if you were flying to Rio, you probably would leave from O'Hare and you'd arrive in Miami and take a jet to get to Rio. And I've done this, so it is going to take you about 7 hours to get from Miami to Rio today. 1952, from St. Louis, probably to Miami, if you recall, Pan American Airways served Latin America. And then you have to get from Miami to Rio. And I'm not sure how many stops there would be between Miami and Rio. And all the time, you're carrying 2 mice in your handbag. Interesting dilemma, isn't it? What do you feed them during this 20-hour trip? I don't know. And I'm not sure how many hours it would take or would have taken in those days to make that trip. What were they? Comfort mice. Yes, yes. There is no account that one of the mice actually got loose in the plane. So that may not have happened. So here she shows up in Rio and at the Institute of Biophysics, and she has these 2 mice with tumor cells in them, and she wants to demonstrate that the tumor cells can actually induce the growth of nerve tissue. And it took her several months to do this. So she had several failures at first, but eventually she did demonstrate that it was true, that the tumor tissue was releasing some chemical that was inducing, triggering, promoting the growth of nervous tissue. And I'll show you a picture of that in a moment. Meanwhile, when she got back to Washington University with these results, they had to figure out what this chemical was. She hired a biochemist named Stanley Cohen, and he was able to isolate this protein that I will show you in a moment, this protein fraction, and they were able to determine that there was a component in this fraction that was the active factor that promoted, triggered, induced the growth of the nerve cells. This is 1953. So some of the methods by our standards today were rather crude, but he was a brilliant biochemist and he was able to do that. And this protein that was the triggering factor, they called a nerve growth factor. Not very creative, but certainly very informative. So what does this nerve growth factor look like? We'll get to that in a moment. She had shown that her findings were correct. The nerve fibers appeared everywhere in the chick embryo's organs like they were supposed to. So the tumor had to release some kind of chemical agent. This quotation at the top says that the fibers that budded out radially from the nerve cells were like flower petals, and you can see these growths on the nerve cell. So the nerve cell is the linear thin portion that goes vertically, and you can see these outgrowths, clusters of nerve cells. And these cells were taken from chick embryos, and they grew in the presence of tumor cells. Well, it turns out that this nerve growth factor is a complex protein. And for those of you who don't know, I'm going to go very quickly through this. Proteins are made up of amino acids. There are 20 of them that make up proteins in all living organisms. And the sequence of these amino acids is very important. It determines a number of factors. So biochemists refer to this as the primary structure, the sequence of amino acids. And if you imagine, if I had one, if I had a ribbon in between my two hands, I could stretch it out into linear fashion. And if you wanted to, you could imagine that this ribbon is made up of a number of units, amino acids, and they're all in a nice straight line. But in nature, it doesn't quite happen that way. So let me show you, first of all, the primary structure of the particular protein in question that they named the nerve growth factor. So starting at the amino end here, there are a number of amino acids that are all listed with their 3-letter abbreviations, serine, serine, threonine, and so on. But you see that it's not linear. It's convoluted. There are reasons for this I won't go into today. And you also see that there are some black spots here. These are bridges. These are 2 cysteine amino acids. There are 2 more here and 2 more there. Cysteine happens to have a sulfur atom in it. When 2 cysteine molecules come in proximity of each other, they can react, form a bond between them that we call a disulfide bridge. They help to give conformation to the protein. So biochemists look at the primary sequence, but they also look at the 3-dimensional conformation of the protein. And as you will see in a moment, it can grow into a very large complex. Whoops, wrong one. Let's see here. There we go. So on the right is a representation of this nerve growth complex. So very quickly, this primary sequence on the left is the blue part here that I'm pointing to. And in nature, a second identical protein buddies up to it, becomes a dimer. So we've got 2 of these that are together, and that is the active nerve growth factor. But associated with it, and this is very common for many proteins, are other subunits. So biochemists have called this blue part the beta subunit. It consists of 2 of these molecules, and they are flanked by 2 of these alpha subunits, which are similar to the molecule on the left, but they have a different function. They have an enzymatic function, and they have a role to play in preparing the blue portion of the protein. So there's these, they're called the alpha subunits, and there are also 2 gamma subunits, and all of these exist in 3-dimensional space, a very large complex. So this is what nerve growth factor looks like. Now, Cohen knew nothing of this. He discovered this factor in 53. Aha, there's a compound, a protein that is the trigger. But it was in later years that others elucidated all these structures. She had other roles in life. She established the Research Center of Neurobiology through the Italian National Council of Research, which played an important role in her life starting in the 1960s. The Laboratory of Cellular Biology focused specifically on nerve growth factor, and she was a director of the lab for a decade. In 77, she retired. Remember, she was supposed to be at Washington University for 6 months. Well, 30 years later, she retired from there, but continued to do research and eventually founded the European Brain Research Institute and served as its president. Now, remember, she's getting older and older now. This is 2002, but she's still active. And she was awarded the Nobel Prize in 1986, along with Stanley Cohen, who was a Wolverine, by the way. And At the time of the award, he was teaching and researching at Vanderbilt University in Nashville, and she was at the Institute of Cell Biology in Rome. So in '86, for their discoveries of growth factors, they won the Nobel Prize for Medicine or Physiology. That brings us, oh, and I wanted to mention, she also did two other things of great importance. She was a person who did social work. She established a foundation that supported women from developing countries. Many of them were African women in finding careers in science. And in 2001, at age 91, the Italian government made her senator for life. And she went to the Senate meetings and she debated on the floor. And up until age 97, she was promoting the sciences and wanted the Senate to approve bills and funds for the promotion of science. So why is nerve growth factor? Well, it can play an important role in Alzheimer's disease, dementia. Now we're talking about nerve cells here. Schizophrenia, depression, autism. It may have a role to play in disorders of viral origin, such as the AIDS virus, HIV, the multiple sclerosis. It's an autoimmune disease. It may have a role to play in there as well. So there's still a lot for us to discover about the nerve growth factor and its implications. Now, I want to point out the last one, the treatment of lesions of the cornea. Apparently, it's been demonstrated that the nerve growth factor, when applied topically, can actually heal some of those lesions. But let me propose something else here. I'll come to it in a moment. Well, I can tell you right now. So she lived to a ripe old age of 102. She remained active and coherent to the end. Apparently, she applied drops to her eyes for years. These drops contained a small amount of nerve growth factor. So people postulated that maybe the nerve growth factor that she was using in these eye drops actually had some influence on her cognition as well. I don't know, but it's an interesting story. So anyway, she did that, but there's one more thing I want to point out about her life other than being in the lab. Victor Hamburger is the man on the left. You've heard his name. And in 1987, they're looking at the medal that's going to be awarded to whoever wins the Fidia Georgetown Award. Fidia was an important Italian pharmaceutical firm. There was a scandal that developed. She had supported the release of a drug called Cronacial. Fidia was making this particular drug, and it was made from cow's brain tissue. There were demonstrations that the drug worked to treat certain disease of the nervous system. But later on, some of these patients developed a very severe neurological syndrome. Most of us only know of this particular syndrome, Guillain-Barré, when we give blood, because the Red Cross asks us in the questionnaire, have you ever had Guillain-Barré syndrome? So apparently these particular patients some of them who had used this drug developed it, and it's a very serious syndrome. The problem here is that Montalcini had supported the release of the drug, and the company, Fidia, had essentially bribed the government. The company had pushed it through. They wanted the government to release the drug so they could put it on the market, and it probably didn't get all the testing it should have. And this scandal was probably a black mark for her for sure. Cronacial was banned in many countries. But yet, this was in the mid-70s, and yet her career continued and flourished, and she still got that appointment to the Senate later on. She was honored on 2 postage stamps. Sierra Leone, that is part of a large souvenir sheet that included a number of scientists. That was issued in 1995. And the country issued those stamps. They were all Nobel Prize winners in 1995. I believe that was the 90th anniversary of the establishment of the Nobel Prize. And the Italians finally in 2013 released a postage stamp to honor her about a year after her death in 2012 at the age of 102. All right. Okay, I'll go quickly through the next one. The last one for today, Barbara McClintock. I'm doing this for several reasons. We started a little bit late, so I'll take a little bit of latitude here with the time. So she too lived to be 90 years old. Barbara had quite a life as well. Born in Hartford at the beginning of the 20th century. Her father was a physician, and her mother was not. She was a housewife, an artist, a poet. They christened her Eleanor. And I don't understand the details. I've not been able to find a good account of this, but for some reason, mom in particular thought that their daughter, Eleanor, didn't fit the name. Was she a tomboy? Was she, the accounts state that she was a forthright child and no nonsense character, but how forthright can a 4-year-old be? But the thing that really struck me is that because the parents thought that the name Eleanor that they had given her wasn't fitting for her personality, they thought that Barbara would be better. So they called her Barbara, and she was known as Barbara the rest of her life. As you might expect, her relationship with mom was not so good. At age 3 until age 5, she moved in with her aunt and uncle. But because she was headstrong, let's put it that way, her parents eventually let her do pretty much what she wanted. And her father, she had a better relationship with her father after he came back from World War I. So Barbara was a solitary person. She was self-sufficient and didn't need a whole lot of socializing. So in high school, the teachers recognized her talent, bright girl, and they envisioned her as a college professor already when she was in high school. Well, mom thought that college professors were bizarre creatures. She didn't think that women should be professionals in any way, because how will you find a husband if you're a professional? So that was her concern. But she wanted to go to school. And when her father came back from World War I, he acquiesced and he put his foot down and let her enroll at Cornell University. So that was right after the war, September 1919. In her junior year, she took her first course in genetics, and she developed a tremendous interest in the field. And interestingly enough, great aptitude, so much so that she earned her bachelor's degree in agriculture, because at Cornell, they did not admit women in the genetics program at that time. Are you sensing a trend here? So she got a degree in agriculture, and she was told by a professor, you've got the aptitude, why don't you go to graduate school right away and get your graduate degrees in the field? So she did. She got her degrees in botany, but interested in genetics of botany. So her personality changed somewhat. She became more social. She even joined the jazz band. I don't know what instrument she played, but she was so popular that she'd been elected president of the women's freshman class. So she gets her degree. She has a PhD now, and Cornell hires her. So she teaches in the botany department, but she also recognizes that there's no future for her there, because there's not going to be any senior faculty position available to her, a woman. So while she was there, she did work in plant cytogenetics. And what that is the genetics of the actual tissues at the, how shall I put this, at the tissue level, as opposed to, if you remember Gregor Mendel, He worked with the peas and he crossed pea plants and he got all kinds of genetic descendants from that. Well, that was one way of doing it, but cytogenetics actually uses microscopy, and you can see in the photograph that I chose here, that puts her at her research bench using a microscope to study the genetics of the plants that she was studying. She focused specifically on the study of chromosomes. She did a lot of work after she left Cornell, partly because somebody recommended her to the National Research Council. Now, 1931 is a depression year. There's not much money to go around, but she actually got money to go study at the University of Missouri. And she also, in 1933, she got money to go to Caltech, and the Rockefeller Foundation and the Guggenheim Foundation provided money year after year for her to study elsewhere or to do research. She did go to Berlin to the Kaiser Wilhelm Institute, and she was not thrilled with what was developing politically in Germany at the time. She did go to Freiburg in 1934, only stayed there for a short while, was concerned about what was happening in Europe, and returned to Ithaca to go work at Cornell. So I just want to give you a little taste of what she was looking at. Remember, her focus was on chromosomes. At the time, they didn't know a lot of things. So she was studying the nucleus. The chromosomes are in the nucleus and of a cell, and they knew that chromosomes carried the genes. Nobody had proven that, but it was an accepted theory at the time. Now we're going back about 90 years, and the role of DNA was unknown. Its structure won't be known until the middle 50s, for one thing. DNA is out there. We know it exists, but what does it do? Nettie Stevens was a biologist at the end of the 19th century. She's the one who, working with mealworms, discovered the sex chromosomes. So you've got the somatic chromosomes for all the other tissues, and you've got the sex chromosomes, which will actually provide inheritance traits. So she published this at the very beginning of the 20th century. So now we know that genes are involved in the inheritance of traits, but they didn't know what they didn't know at the time. And because of various studies, we knew that the number of chromosomes vary from species to species. She chose to work with corn. There were several reasons for this. Well, first of all, she had degrees in botany. Corn has some properties that can be easily tracked. And she did a lot of experiments, and I will show you one critical one in a moment, that could where she could easily observe genetic changes. And the one drawback with this is that you can't grow corn instantaneously. It's not like a fruit fly where you can get a new generation of fruit flies in a very short time period, a very short period of time. So she had to deal with yearly cycles of corn. This is the significant experiment that I want to show you. Corn has 10 chromosomes. And because of her microscopic studies, she observed that one of these chromosomes, number 9, has, there it is. So has actually a knob at the end and is rather elongated compared to other chromosomes. And she worked with a student named Harriet Creighton on this particular experiment. The black bar on the right is a normal chromosome, and the geneticists use these markings to determine traits. So the lowercase c means colorless. For us, we'll call it yellow. We know about yellow corn. And the uppercase W, lowercase x is normal endosperm. The endosperm is the starchy part that we bite into in the corn. The endosperm consists mostly of starch, And starch consists of two molecules, amylose and amylopectin. They're made of glucose, just regular glucose, but the conformations are different. The ratio of amylopectin to amylose is characteristic. So it is different in wheat than it is in rice, than it is in lentils, and it's different in corn. So the chromosome on the right has the normal endosperm, this one here. The one on the left has what is known as waxy endosperm. The only difference here is that the ratio of amylopectin to amylose is much higher. It's 85% amylopectin, 15% amylose. And they call this waxy because it gives it a different texture. And she used purple corn, and that's the large uppercase C here. Why am I showing you this? It's because of this experiment. Look at the top portion, and you've got these chromosomes here. What she observed was this crossing over from one chromosome to the next. And if that's happening, she's going to observe 4 end products. And she did. So this one here is the extra long chromosome with the knob at the end, the colored, the purple waxy one, which she started with. She also saw some corn that looked like the normal colorless, or in our case, yellow, normal texture. But she also found the colored purple with the normal texture. And she also found the colorless with the waxy texture. And that, she explained, could only happen if there was crossing over of these gene components. So this was evidence of a physical exchange of parts of the chromosome. This crossing over was one of her 2 big accomplishments. So moving along quickly here, she had a long career. I mentioned that she had gotten money from Rockefeller Foundation and the Guggenheim Foundation, and she eventually found herself at the University of Missouri until there was no job for her anymore because her mentor left. She was told, "You're going to be next to go." So she left. And because of her reputation, she got elected to the National Academy of Sciences, and the Genetic Society of America made her vice president and then finally president herself. She was invited to go to Stanford to identify the chromosomes of Neurospora, which is a mold. And she was recognized as, in her field, as the best. And George Beadle invited her to come and help him identify the chromosomes of Neurospora. Now, finally, the last thing I want to mention about her would be the work that she did in the latter part of the 1940s. Her study of what she called controlling elements. I'll go quickly through this. You recognize a double helix of DNA. It turns out that she discovered that there was a part of the DNA strand that was movable. We today call it a transposon. She called it a controlling element. So this transposon, this blue section here, actually will be cut away from the DNA. The DNA portion here is going to come back together using some existing enzymes in the cell to heal it, as it were, to repair it. And this portion here, which has been excised, is going to find its way into another part of the DNA. This is an enzyme that is present here. It's going to cut away at a specific location, the DNA strand, and it's going to insert itself in a different location. It's a mobile element. This was quite revolutionary. So you have the excision from one strand, it drifts to another place and gets integrated into the recipient DNA section. So let me show you very quickly the anatomy of a transposon. This is the blue part you saw a moment ago. This is actually a the nucleotides in the DNA that will code for an enzyme. The enzyme is going to cut specifically at these points because the segments of nucleotides are very specific. Only 5 pairs are shown here, but actually there are 31 pairs in this section on either side of the area that's going to be cut away. And these 31 base pairs are not only specific, they're a mirror image of each other. And this portion here, the transposon, is going to leave this section of the DNA, and it's going to drift and find a recipient site, a very specific site, and implant itself in there. Now, this is a very common occurrence. It happens, as we found out, in almost all organisms, which is very surprising because you would think that a cell, an organism, wouldn't want to have this kind of mobility going on for fear of causing mutations, deletions, or insertions in the wrong place. Well, these things have happened in our DNA. Our genome shows that transposons have been around for a long time and that they actually have been incorporated into our DNA, and yet we're still here. So I'll go through this so that we can conclude. She explained how complex organisms could have this kind of variety because of these mobile elements. It's inducing some of the variety in the DNA, but she didn't publish it. She thought it was too radical. People wouldn't believe her. But she did present it at a 1951 symposium, and she got minimal reaction. Now, there are, again, different accounts about what happened. Did they ignore her? Did they not believe her? Did they not understand her? That's another possibility as well. So I want to read this to you because she, back in the late 60s, said that we are sadly ignorant of the organization of the chromosome and of the possible types of changes in this that may occur as a whole or at a specific site. We're beginning to learn of some types of change, and these are producing surprises. I am convinced that we should expect some startling surprises in the future. And for those of you who have been in the medical field or related to the medical field, you know that this is very true. So this was some 55 years ago, 57 now, and we've experienced a lot of changes in this field and learned quite a bit. So again, at age 81, in 1983, she was the sole recipient of the Nobel Prize in Physiology or Medicine for her work on mobile genetic elements, known as transposons now, the process of transposition. I said sole recipient because it's so common that 2 or even 3 people share the award, but not in 83. They gave it to her, but this happened decades after she had actually done the work. In 1971, President Nixon gave her the National Medal of Science along with other scientists, and that day he said, "I have read explanations of your scientific work addressing all the scientists in the room who are getting the medal, and I want you to know I don't understand them. But I want you to know too that because I do not understand them, I realize how enormously important their contributions are to this nation. That, to me, is the nature of science to the unsophisticated people." And here are 2 tributes to her. Up upper right, the earlier one, 1989, you recognize a lot of elements here that made up her life. The corn that she studied, the chromosomes just above the ear of corn, the transposition. This is the kind of work that she did, and it's represented on this 1989 stamp. How many of you remember the lower left stamp that was issued a mere 19 years ago already? Barbara McClintock was one of 4 American scientists in this series, and I take it from your looks that you don't remember it very well. You may not have rushed out to the post office to buy them. So McClintock was, in fact, honored here in the US on a postage stamp. So I will leave it at that. I know it's late. We started a little bit late, and if you have any questions or comments, I will be here afterwards if you wish. I can stay.
Thank you, Louis.
To research what?